Okay, so welcome everyone for this presentation, which is given by Perttu Hilla on his master thesis. And this master thesis was given the best master thesis in computational chemistry in Finland 2022 award by Computational Chemistry section. So go ahead, Perttu.
Okay, thank you, and hi everyone. So yeah, today I will talk about my master's thesis and also a little bit about some more recent stuff I've been doing during my PhD studies, but mostly focus on the master's thesis things. And first of all, thank you to the computational chemistry section for giving me this opportunity to share the stuff and talk a little bit more about those. So yeah, just making sure this is, yeah, I think it's visible since no one said anything. So, okay, yeah. So molecular dynamics and NMR chemical shift of xenon in cryptophane-A is the topic of today's talk. Let me see, can I? Yes. So first of all, I want to say a few words about NMR or nuclear magnetic resonance, because not everyone here is doing NMR, and these xenon biosensors or these structures that we're studying are related to NMR. So one could say that NMR is a spectroscopy of nuclear spins. We use external magnetic fields to manipulate the orientations of the spins. And by recording the response of these spins, we get some information on the microscopic environment of those nuclear spins, because the response is very dependent on the chemical environment in which they're in. So different spins or different nuclei in different parts of the molecule might respond differently. So it's a signature of the molecule. And the good thing is that these transitions between those nuclear spin energy states corresponds to radio frequency waves. So by using these external magnetic fields, or which are in the radio frequency range, we don't actually disturb the sample as much as in some other spectroscopies, which is a good thing. You get sort of an unbiased response from the sample. And also it's non-harmful for tissue. So magnetic resonance imaging has sort of revolutionized magnetic or medical imaging, and that uses NMR. But on the other hand, since this energy difference is so small at practical temperatures in room temperature, the thermal energy available induces or easily induces transitions between these levels. So the Boltzmann population of these different energy levels are almost equal, and in NMR, the intensity of the signal that we record is proportional to these population differences. So we get a really low sensitivity in NMR as it's conventionally used. So modern NMR is all about this hyperpolarization in which you sort of try to, let me see if I can, yeah, you try to increase this population difference between different energy levels. And in particular for xenon, xenon atom or xenon nucleus, there's something called a spin exchange optical pumping method, which can be, or for xenon, using that we can easily achieve this hyperpolarized state and a pretty high signal through that. And this can be combined with some other experimental methods which are not so important now, but the important thing here is that we need some kind of chemical exchange between two different states or different environments, and that will become important later. And also using xenon is motivated by its chemical sensitivity. So as I said, the response of the nucleus depends on its chemical environment, and this is what we call in NMR chemical shift. And xenon is extremely sensitive to its chemical environment, and that's why it's used a lot for probing, for example, porous materials or some kind of molecular cavities. And this is just an example. Later we will actually talk about what these systems are, but you can already visually see that these different environments, even if this xenon atom in green is not binded to anything, it sort of reports a different signal on these different chemical environments. And this is a useful property of the xenon atom. But a problem is that since xenon is a noble gas, it's chemically very inert, so it's hard to achieve molecular selectivity because it doesn't really bind with the target you would want. So one approach to overcome this issue is called xenon NMR biosensors, originally reported in 2001 by this Pines group. And in here, you use this host molecule to encapsulate xenon and apply it as a biosensor. So in this structure, there's this functional arm attached that is designed to bind with some target molecule. So you don't have to worry about xenon being an inert gas. So yeah, essentially in experiments in solution, you would have this kind of two different chemical environments, which you distinguish in the NMR spectrum. And then when you have some target molecule that you would want to study, as I said, these functional arms are designed to bind with the target. And as a result, the chemical structure of this biosensor changes. And this is, of course, carried out to the electron cloud of xenon. And because it's so sensitive, it also detects this chemical change in the structure. And therefore, the xenon nucleus also sees this binding event here. So we can distinguish these two different environments also in the NMR spectrum because xenon is so sensitive to its chemical environment. So I like to think of xenon as some kind of lighthouse or microscopic lighthouse that's sort of scanning over the entirety of this biosensor structure. So if everything goes well, we have a sensitive method with high resolution and molecular specificity, but of course, there's still some issues. So what are these host molecules? One, or currently the best, I guess the best or most common category are called cryptophanes. They are these sort of two bowl-like structures connected to each other by these linkers, and there are these portals, or maybe I should have had linkers here, but essentially you have three linkers and three portals between these bowl structures, and then there's 6 functional arms attached to the structure. And in my master thesis, we used this cryptophane-A structure that, or cryptophane-A molecule that encapsulates xenon. And in here, the functional arms are just CH3 units. I don't have the hydrogen atoms here visible now. And these linker groups are well, they have this chemical structure. So it's a sort of a symmetric in that sense that everything is the same. So what affects the properties of xenon biosensors when we would want to apply these? So there are, I guess, 3 important topics that one can talk about. Is first of all the affinity of xenon. So what's the free energy of binding? Because we want the xenon to bind with this host structure. Then it's important that some kind of exchange occurs, that xenon doesn't stay too long inside the host structure when it's in solution. And this is important for the hypersest method that I mentioned earlier. But you just or the important thing for us is that some kind of exchange between the xenon bulk and the host structures has to occur. And then of course the NMR chemical shift. So the host and the solvent affect to all of these 3 properties. For example, the structure and interior of the host, of course, affects how xenon binds to the structure. Then the solvent can possibly compete with xenon, and because we talk about free energies, one would have to know what does it mean when you talk about an empty host structure. Is it actually empty, or is there some solvent molecules maybe bound with the host structure or something? So exchange of xenon for this, the portals, as I just showed, and the functional arms are important. Do those affect the path and rate of exchange? what's the role of individual solvent molecules, and then for the chemical shift, of course, the electronic structure of the system dictates what's the NMR chemical shift, and solvent can also induce pretty high modifications to this. So yeah, all of these are kind of microscopic details, and these should be well known, and this kind of motivates the computational approach. So the topics of my master's thesis were to find out for these xenon cryptophane-A structures what's the free energy of xenon binding, and this corresponds to the affinity. Then the xenon complexation mechanism, how does the xenon guest leave the host structure, what is its path, and are there some mechanism involved? And then, of course, the solvent dynamics, and what's the role of water molecules as solvent? And then now more recently in my PhD studies, we have looked at the NMR properties. So what's the chemical shift of xenon inside these host structures? So the first one, free energy of xenon binding, we used what's known as a thermodynamic cycle method. So what you do is, to get an idea of the free energy of binding, you simulate different chemical systems or different physical systems, and calculate their total energy averages, and then subtract them in some or the correct order to get an estimate on a binding energy. So here we simulated just water, then xenon atom in water, then the cryptophane-A host structure in water, and then this biosensor structure in water. And when you get the total energy averages and subtract them in this shown order, you sort of get an estimate on this binding energy as I've shown here. Of course, there are some more elaborate methods, but this is sort of the first approximation, let's say. So we use this pretty new XTB software. It's a density functional tight binding based software for the MD. It's not so important what this means. And we wanted to compare, well, 3 levels of theory. There are this GFN2 and GFN0, and it's just important to remember that these are what's known as semi-empirical, I guess you could say Born-Oppenheimer MD, in the sense that for each configuration, you solve the electronic structure of the system and use that in the Born-Oppenheimer sense to drive the nuclear dynamics or the motion of the nuclei. Yeah. So these are sort of quantum chemical or semi-empirical methods, this GFN2 and GFN0. And then there's also this GFN-FF, which is just more of a classical force field method. So we wanted to compare these 3. So the results in the literature, the values for the free energy of xenon binding experimentally maybe from 4 to 6, and computationally there's a bit wider range of values. So yes, our results, we see that the GFN-FF and GFN0 produce pretty good results, especially the GFN-FF level, but the GFN2 kind of overestimates the binding energy, so it's too attractive. So in the overall, at least each level of theory produces the attractive sign, and in particular, the GFN2 seem to overestimate this value. And this is most likely related to the fact that since it has been reported that these XTB Hamiltonian or this GFN2 Hamiltonians kind of overestimate the attraction between noble gases and some other atoms, so this would explain the overly attractive results. Okay, then the second topic was the xenon complexation mechanism, which is related to the exchange process. So experimentally, this exchange rate lies somewhere in hundreds or thousands of occurrences per second. And in typical MD, as most of you probably know, the time step is of the order of 1 femtosecond. So this would take years, and normal MD is practically ruled out. So then there exist these methods for enhanced sampling, and one of them is metadynamics. And here you use this, as the simulation evolves, the MD simulation evolves, you use this bias potential energies along the phase-space trajectory of the system to discourage it from entering previous configurations, okay? So as time goes on, the metadynamics engine drives the system to other regions in the potential energy surface. And therefore you explore new conformations and new reaction paths and so on. So in our case, we used MTD to push xenon atom out from this host structure. So we begin from a xenon atom inside this cryptophane, and then we use MTD to push it out. And it's important to note here that it's not a force acting on xenon, but rather it's just enhanced sampling of the phase space, and eventually xenon should pop out of the structure. So what we found out was that there's essentially at least essentially 3 different processes, and we see that water molecules actually initialize each of the processes. And of course, this is not an exhaustive list, but in our finite number of simulations, this is what we saw. So process 1 is pretty simple. Water molecule comes into the structure, interacts with xenon, and the xenon atom exits. So here's the actual MTD simulation. One water molecule comes in and almost carves out the xenon from the structure. So this is quite interesting. It's not actually the other way around, but instead the water molecule first enters and then xenon comes out. And the process 2, you have 2 active water molecules. They interact with xenon and xenon comes out. And again, the actual MTD simulation here. And one of the water molecules also exits in the end. And then the third process is a little bit more involved. There's 4 water molecules active. 2 of them first sort of initialize the process, poke the xenon atom a little, and then the 2 remaining water molecules push the xenon atom out eventually. So again, here's the MTD simulation. Yeah. So this was reported by us for the first time, this kind of getting a qualitative idea of the exchange process. And here's just some plot of distances of the water molecules and the xenon between, or with respect to the center of the cryptophane cage. And here's the sort of the parameter of the host structure. So we indeed see that the water molecules first enter, and there's this brief coexistence period of about 4 picoseconds in the structure, and then xenon atom exits. So and the host structure changes its conformation during these processes. It's a combination of the sliding and French door mechanisms. And in the sliding door part, the portal sort of stretches its bonds, as you see here. And then in the French door part, these CH3 groups rotate away from xenon, or after xenon has come out, they again close the portal, one could say. So we see that the dynamics of the host and explicit solvent molecules actually play a really important role in these processes. So then the third topic was water dynamics and solvent effects. And as we already saw, water molecules play a really important role in these exchange processes. So one could ask, well, is the host structure even empty to begin with in the simulations, or is it filled with water? And well, you can pretty easily already see just by looking at the trajectories with some visualization program that indeed there is water, that the host structure actually encapsulates also water. So then you could ask, what kind of dynamics does water undergo with this host structure? So now we don't have xenon here, it's just water molecules and this cryptophane cage. So we did some MD trajectory analysis on this water dynamics. Yeah, and this is restricted only to the GFN0 and FF levels that produced good binding energies, because the sort of on paper best method is of the GFN2 was also computationally the heaviest. So there was not enough trajectory to do this analysis. So we only have the 2 methods now. So yeah, here's a plot again between the distance of water molecules and the center point of the cryptophane. So we see that there is indeed a lot of exchange between the bulk water and the bound water going on. And at this GFN0 level, this dynamics, especially at the perimeter of the host, is pretty fast. There's from 0 to 6 water molecules inside the host, and then on average about 3 molecules in the host structure. And then on the force field level, it's a bit slow. Sorry, yeah, it's a bit slower dynamics. And from 1 to 4 water molecules reside inside the host, and then on average about 2 water molecules. So yeah, this kind of shows, oh yeah, this is one nanosecond of trajectory in each plot. So it kind of shows that there is a lot of exchange going on between the bulk and the water. So of course, then you would like to know what's the mean residence time or occupation time of water molecules. So you can do this, what's known as survival probability function. It's just a time correlation function for the residence of the water molecules. And then you can fit an exponential decay to the numerical values that you get from this. And this you get from the MD trajectory. So yeah, this with time equals 0, you get the value for the average number of water molecules inside the host, which agrees with what I just showed. But these are the interesting ones here. So yeah, on the GFN0 level, again, it's a bit faster dynamics, about 200 picoseconds of mean residence time for water molecules. And on GFN-FF, it's about 300 picoseconds, so a bit slower dynamics. And this all kind of makes sense because as we earlier saw in this thermodynamic cycle method, since we're now talking about this third system here, or maybe I should have added a water molecule here because now we now we know that there actually is water molecule inside this. But anyway, since on GFN0 it was too attractive, this xenon binding energy. So if this structure is not as organized or as ordered as it is on this slower dynamics timescale, then the way it affects in this thermodynamic cycle would be or is exactly as we saw, that the xenon binding appears energetically overly attractive if this one reference site differs also between these structures. So it's not only about how xenon is bound to the host structure in here, but also what is this reference structure shown here. So it's important to know what water molecules or the solvent molecules do with the structure, with the host structure. So yeah, this was my master study, master thesis topics, and if you're interested, there's a publication about this also. So, and then some more recent things during my PhD studies for almost, or let's see, a bit more than 1 year now. So we wanted to then move on to the NMR properties or the NMR chemical shift of xenon in these 3 different environments. And now we also included, we had xenon in water, then this cryptophane-A structure, and now we also included this water-soluble cryptophane-A derivative, where you change the arms or the CH3 arms to this acid units with which help with the water solubility of the structure. So as I said in the very beginning, the response of the nucleus to magnetic perturbations, which we use in NMR, is determined by, of course, the electron cloud of the system, or near the nucleus. But you can't do just sort of normal quantum chemistry, because xenon is a heavy element. So there's 54 protons in the nucleus. So the core electrons experience a very strong Coulombic force, and it happens near the nucleus of which we're interested. So this is important. And the velocities, I guess you could say that the velocities become comparable to the speed of light. So you must include relativistic effects, and then one talks about relativistic quantum chemistry, which is also quite a common practice nowadays. So as we had the molecular dynamics simulations, we wanted to do motional averaging of xenon chemical shift. And in NMR, this magnetic response is called nuclear shielding tensor. And it's just a 3x3 matrix. We get it from the quantum chemical calculations. And in our case, we used turbomole. It has this so-called exact two component X2C relativistic corrections for NMR properties. And this is kind of an efficient way to get closer to the actually relativistic values in an efficient way. So we averaged this nuclear shielding tensor over hundreds of MD snapshots, which means that for each snapshot, we extracted, of course, those systems were too big, so we extracted smaller clusters and then calculated the nuclear shielding tensors for each snapshot, and then you can do an average over that ensemble. And if you have enough statistics, then this should be comparable to the experimentally measured value. But I guess the interesting thing is that since thermodynamic properties were affected by system dynamics and solvent effects, then of course, how about xenon chemical shift? Is this affected by this stuff? And if one would know all this, then I guess the sort of dream or whatever it could be this fine tuning of xenon biosensors, that if you knew how this chemical composition of the host structure and the solvent affects this thermodynamics and then also the chemical shift, then you could sort of fine tune the structure and find a structure that would best fit for some particular application. So it's important to know this stuff. And also we wanted to outline the computational workflow that's required to do this motional averaging in this kind of complex and highly dynamic systems. So without going into too much details, I just wanted to show the main results here. This changing the CH3 arms to these acid arms induces a change of about 30 parts per million, and this is a measure we use in NMR, but in general sense it's quite a lot, since it's not very close to the xenon, these arms, but rather far away. But since xenon is so sensitive, you can see this change quite clearly. And then the interesting thing is that we found out that xenon chemical shift is actually linearly dependent on the number of neighboring atoms, or the coordination number around xenon. So if you plot, or of course on average, so if you plot the coordination number or the number of neighboring atoms as a function of chemical shift, or well, the other way around, so a chemical shift as a function of the coordination numbers, yeah. So, and here you have each snapshot and the corresponding chemical shifts with this particular coordination number, and then you plot everything, so you sort of get a linear trend here. And this same, of course, I have more data here, but the same trend seems to hold for each structure on average. Oh yeah, and these are the structures that we correspond to these plots. So this was earlier reported for static xenon clusters, and now we see that this kind of very simple trend also holds for these highly dynamic and flexible xenon biosensor systems in water, which is kind of surprising. So what's going on then? And this is I'm just showing a very naive interpretation and some table of contents graphic that's not quite ready yet, but let's see. So you can use this non-relativistic expression for the xenon, or the paramagnetic shielding constant, and this kind of determines the chemical shift of the nucleus. So here you see that it's proportional to this orbital angular momentum operator, which requires a symmetry lowering of the ground state so that it couples these the excited state and the ground state of the system. So there has to be some sort of disturbance around the electron cloud of xenon. And since there is an R to the -3 dependence, it has to happen quite close to the xenon nucleus. And this is what I've shown here. So in this kind of very spherical environment inside the whole structure, there is a low xenon chemical shift. And then when some atom, for example, of the linker group of the host atom comes close to xenon, there is this symmetry disturbance around xenon, which then increases the chemical shift. And for example, in water solution, there's many of these disturbances occurring. And we call these disturbances paramagnetic channels. So because increasing number of atoms near xenon increase the number of paramagnetic channels, which increase the magnitude of this paramagnetic contribution to the shielding, this directly affects the chemical shift of xenon, and this is why we see this sort of linear dependence, as I showed in the last slide. So this is quite interesting and also very simple, I guess, interpretation. So okay, that's all I had to say, and I still wanted to say a special thanks to a few people. So Juha Vaara in particular for supervising all of this and having the ideas, and then these people for nice discussions about work and also about other stuff. So thank you.